What is the minimum value of the expression x plus 4z as a function defined on R3, subject to the constraint x squared plus y squared plus z squared less than or equal to 2? Okay, there are a few things that come to mind on how you might approach this problem. The first thing that jumps in my head right away is to treat this as a constrained optimization. So we have a function x plus 4z, which is a function of 3 variables, if we, even though y doesn't appear. And we have a constraint x squared plus y squared and so on. So we can set up the equations that we need to be satisfied for that constrained optimization. But the other thing I'm going to recognize is that the function we're optimizing, minimizing in this case, is linear. And the set that we're minimizing over is a sphere. It's the surface and interior of a sphere or ball. Now, if you think of the level sets of our objective function, x plus 4z, if I set that equal to a constant, then the set of points making that equal to that constant is going to be a plane. And as I change the constant, the plane will translate itself. And if you think of what the geometry of this looks like, then what I want to do is I want to find the largest constant such that the plane, the corresponding level set, still intersects the sphere. So I don't have to worry about the interior. I only have to worry about the surface of the sphere. I mean, if I draw a picture for this, if this is the sphere that I'm worried about, if I set the function x plus 4z equal to a constant, then I have a plane. It'll either slice through the sphere or it won't. So I'll say that this is x plus 4z is equal to a constant. Now, as I change this constant c, as I change that, the plane simply shifts itself. It translates. And what I want to do is I want to find the value of c as small as possible, such that when I translate the plane, it still intersects the sphere. So that, of course, is going to happen when I intersect. Okay, and I also noticed that the value of y, because the value of y does not matter, is that going to affect anything? If the value of y doesn't matter, am I just going to end up setting y equal to 0? Well, anyway, let's go like this. F of x, y, z is equal to x plus 4z. And I also have my constraint, g of x, y, z. I'm not going to write it as an inequality. I'm going to write it as an equality. So this is x squared plus y squared plus z squared. And this is going to be equal to 2. So if I want to make this small, then x and z should both be negative and as negative as possible. But if y is non-zero, then I have to decrease the magnitude of x and z, or x or z or both. So it's enough to assume that y is equal to 0. So I have x plus 4z that I'm trying to minimize, subject to x squared plus z squared is equal to 2. So now I'm thinking about treating this more geometrically and drawing. So I could cheat here. The way I could cheat is I'm given multiple choice options, right? So I could set x plus 4z equal to one of the multiple choice options, one of the negative options, and then just make sure that the value of x, that the line x plus 4z is equal to a constant, make sure it intersects this circle tangentially. I'd rather just actually go through the computation and solve for this minimal value. So do I want to do it with geometry, or do I want to set up a system of equations to solve? let's get out of my comfort zone and use some geometry. Okay, so this is going to be the x and z plane. Again, I'm only worried about negative values of x and z. So I have x plus 4z is equal to a constant. I'll write this as z is equal to c minus x divided by 4. So when x is 0, sorry, why did I write 2 divided by 4? So when x is 0, z is c over 4. And we have a slope of negative 1 over 4. Okay, so when z is 0, x is equal to c. So c is negative. We expected that, right? C is going to be a negative number. And I want to draw here a circle of radius 2 such that we're tangent like that. So that point is at negative 2. That point is at negative 2. Okay. So maybe I could just take this point there and call it something. And I know like a dot product of that vector and that vector is 0. Is that the best way to do this? I'm going to call this px, pz. Call that a vector. So px, pz dot. I mean, there's probably some kind of like projection formula or something like that to get the magnitude of that vector. Maybe that would be a faster way of doing this. And this vector here, that's going to be c comma 0 minus 0 comma c over 4. So that has to equal 0. So I have px times c minus pz times c over 4 is equal to 0. So px is equal to pz over 4. And I also have that this point lies on the line. That doesn't find the value. That doesn't find the vector c, does it? Or the value of c. Well, I also have that px plus pz over 4 is equal to c because it lies, sorry, plus pz. Wait, yeah, that's equal to c. Okay, so that's three unknowns though, and I mean, obviously I have p squared plus px squared plus pz squared is equal to 2. Yeah, maybe that'll help. This does not seem to match any of the answers I'm given, especially considering, yeah, I've got some positives and negatives completely mixed up. Oh my goodness, I've messed this up royally. I wonder if it's just a result of a sign error somewhere. So PZ is in fact negative 32 over 17. PX, well, let's make sure I did the algebra there correctly. I don't even need all this dot product jazz was completely needless anyways. Let's just call this P and Q. Okay, so I've got P squared plus Q squared is equal to 2. And I also have that it's on this line. So P plus 4Q is equal to C. I don't understand why I'm getting numbers so different, something so different. Do I have an arithmetic mistake somewhere? Finally. I don't know why this took me so long. I don't know if I had arithmetic mistakes in places. Or what? Yeah, I don't know why I had arithmetic mistakes is all over, or why I was getting the wrong answer. Well, here, I mean, I did that wrong, right? I just said that's Q, but it should be 4Q. I don't know what I did wrong up here. Probably something along the same lines. Oh my goodness. I mean, every approach that I mentioned does end up working here. Doing things with geometry, if I didn't make these mistakes, would have worked. I eventually just, laid back on the stuff that I am more comfortable with, and my first approach. Think of it as a constrained optimization. So I have a Lagrange multiplier, go through the system of equations, and don't make arithmetic mistakes. So there I go, negative root 34. Oh, this was pretty bad performance. I mean, I guess the key here is recognizing that when you're maximizing or minimizing a linear function over a convex set, then the optimum will be attained on the surface of that convex set. So yeah, that simplifies the question, and it should have been easier from there, but I mixed this up big time. If this is the wrong answer, then I'll have a comment somewhere on the video. Thanks for watching.